Good morning, everyone. How are you? Big wave hello. Show me the love. Show me the love. Thank you all for coming again. Or rather, thank you for coming back. I guess many of you could have decided, heck with this guy, I'm out of here. I mean, that could happen too. So who knows? So I'm glad you all decided to come back and share things today. Okay. Everybody thumbs up. Everybody can see the PowerPoint, right? It says the thank you. Okay. So as we always do, we kind of go through the announcements of the day, right? So again, welcome for coming. Again, just to remind everybody that when you send me an email, make sure you put the QM221B1 in the subject line so I know who you are and what we're doing today. And again, we want to send some video recordings for those of you who are, excuse me, introductions, right? I've got a few. I didn't get any volunteers from the audience yesterday, so we're not going to be having student introductions today, but we will start tomorrow. So I'm going to be pointing to a couple of people that are going to go tomorrow. Yes, Eliza, thank you for volunteering. I love it. And Ryan Negan, you can go tomorrow too for your student introduction. So tomorrow is the day for you too. Thank you so much for volunteering. Max, guess what? You're also going tomorrow. Thank you very much. So you're all set to go. So you are my 3 going tomorrow. Okay. And I will send out the other form for people to fill out. So that's great. Okay. So here's our agenda for today. Okay. My first question is, were you paying attention? Please show me your red pen. Okay. All right. So thank you. Right. Silly little exercise. But again, the point of what I'm trying to instill upon you is so many times I know you get into this rut, if you will. You go to class and you know there's going to be PowerPoints and you know the teacher's going to lecture or whatever, but you don't really pay attention and tune in. That is definitely not the way to take this class. In this class, you've got to hang on every word that I say. And I don't say that to say that I'm egotistical and that, you got to listen to me. But I am going to impart information that I am going to say only in words, right? I'm not going to write it down. Again, I do say things 3 times if it's important, but some of the subtleties, and the subtleties are on what's on the exams, are the things I kind of mentioned. And again, this is all choreographed. I've done this so much, I know exactly what I'm going to say at 9 minutes and 58 seconds into this class, right? I know the joke I'm going to tell, right? So again, I know exactly what I'm going to look for, and people that pay attention and want to get A's, that's what they do. They're paying attention. Now, again, you do not need to go back and look at the recordings. That is a wrong thing to do, right? You need to make sure the understanding that you are preparing yourself for business, right? That's what we're doing here. This is a real world class. I come from industry, right? I was a consultant and am a consultant for years, right? So I am not just an academic. So I'm not coming to this class strictly as a professor. I'm coming at this class as somebody who has business knowledge to teach you how to behave and what you need to do to get a job, right? That's exactly what I'm doing, okay? So again, you want to have the subtleties of stuff. So the red pen. Now again, you're going to come to me, you're going to get a question wrong on an exam, and you come talk to me about it. I'm going to say, remember the red pen? They go, oh, that's right. You did mention that in class. Oh my gosh, I forgot. Well, don't let that be you, okay? So again, it's all about being engaged in this class time now. Again, it's unrealistic for you to go to this class for 2 hours, then to watch the video for another 2 hours, then do the homework. That's too much time. Again, you've got to be efficient with your time. Again, you have other lives and other things you do. I mean, work is only part of what you do as a human being, right? Okay. All right. So today we're going to do the probability homework in just a few minutes. Then I've got a couple exercises to do. They'll be fun to talk about some things for probability. Then we're going to talk about have a break. And then I'm going to launch into my Bayes rule PowerPoint today. Again, that's not real long. And then, again, I'm not sure the KPOTD, I'm not sure I'm going to have it for today or not. But again, generally speaking, at the end of class, there is kind of an assessment that will kind of be done. It may not be ready for today. So we'll see how far we get. Okay. So any questions before we begin? Everybody kind of knows what we're doing. Everybody understands what they have to do for the video introduction, all that sort of stuff. So Eliza, right, Ryan, and Max, clearly, if there's a question, talk to me in the class. Again, Don't be nervous. It's fun, right? It's supposed to be fun to do this. Make sure to do some interaction, right? And again, I do want to encourage you all to kind of reach out to other people in this class. Again, there may be other people that you may have remembered from being on campus, right? So I definitely want you all to think about forming a study group, right? By the way, Max Sweet Bomb is the one that's going tomorrow, not the other Max, not Max Zhao, right? So Sweet Bomb is where you're going tomorrow, okay? All right, so what I'm going to do is I'm going to stop screen sharing my video. Now you can all see me clearly. Hello, everyone. Nice to see you. So again, you can see me in my lair here, if you will. It's very funny, actually, because obviously with this going the pandemic and BU basically going to online teaching, it's funny now, obviously, and you kind of look back and again, I certainly hope you all are safe and all that sort of stuff, and certainly hope you are still paying attention, because the virus is still real. There are things we still need to do, but it's kind of funny because obviously here at BU, most of you know that this transition happened all over spring break, and the funny thing was right before spring break. Unfortunately, my wife has an aunt she's very close with that died like the week before spring break, right? So my wife and I were due to go away for spring break, like many of you, and because of the funeral, we had to change our plans a little bit. So we had to go down. We basically left a couple of days early for our vacation, to come back early to go to this funeral, right? So. And obviously you remember the email. So back in, this is March 15th or whatever, or March 10th, you get an email saying, oh yeah, things are, we're going to start looking at the coronavirus. It's coming out, blah, 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 right? All this sort of stuff. But as faculty, we get an email. The email is, okay, this is serious. University of California and somebody else has already gone to online teaching. So this is probably a discussion that we need to have, right? So then Saturday of spring break, so you guys are all on your spring break, I get an email, yep, we got to talk about this. We're going to set up meetings for like 2 weeks after we come back to see if something's going to be done. Tuesday, email comes out, yeah, well, it looks like a little more serious. We got to talk about this thing. We may need to move that meeting till the week right after spring break. And then like Wednesday, yeah, it's getting pretty serious. So I think we may have to really think of what we're going to do and see if we can talk online. Thursday, we're starting Monday, be ready. I'm like, what the heck? I'm on vacation, no Zoom, no nothing. And my point of my story is behind me, you can see there's things on the walls, things down here, but this is basically, this used to be my nice office. I haven't really been down here in a long time because I've worked out of BU for so long. This was filled to the gills, to the ceiling with junk. Again, one of my businesses is a flooring contractor, right? I was a hardwood flooring contractor. So I had a lot of hardwood flooring products. They were all behind me. It was floor to ceiling. This was basically my storage room. So the first day I started Zooming in my class, the students see all this junk. They, what, are you in a storage room? What are you doing here? And then each week, things get more and more cleaned up. So if you actually look at the videos and watch the progression, you can see how well the room kind of became a living space. So it's kind of fun. Anyway, I digress. But again, I want to get you all warmed up. I know it's only 9:08 in the morning. Make sure you're all kind of awake. So let me have a sip of my coffee, right? You want to get out your homework? We're going to start with problem number 1 in about 30 seconds. Okay. Now, normally what I'm going to do, here is my document. Here's my homework like you guys have. Normally, I'm able to have this and show this on my document camera. But with this one assignment, it was taking too much effort to kind of rip apart the PDF file. So unfortunately, I am going to go to my document camera and do the problems, but I'm not going to have the questions to refer to. Okay, so you need to make sure you have your questions for what you're doing. And again, you're not turning anything in. This is, again, you are adults, right? The idea of this is you are now mature enough to do your own studying. I shouldn't have to watch you and have you turn in the homework. That's ridiculous. I mean, you should know what's going on. Again, this is for your benefit. You're going to get the grade, not me, right? Okay. All right. So first question, right? I'm reading from the assignment. If the stock market index goes up 70% of the time, what percent of the time does it go down? Okay. So please, someone raise your blue hand. I want to call on somebody and somebody give me the answer. This is problem number 1. This is a way to start the semester. Yip, yip, yahoo. Oh, Eliza, you're first. Please tell us the answer. The answer is what?
0.3.
0.3 for 30%. Okay. All right. I want everyone everyone, I want, if you believe Eliza is right, and you agree with her, raise your blue hand, right? Please do it right now. Put your blue hand up there if you say it's 30%, right? Okay, keep going, right? Everybody should have their hands up. We're sure they're doing the right answer, right? So if you don't have your blue hand up, I'm going to call on you and I'm going to ask you, if you don't like 30%, what are you going to tell me the answer is? Okay. All right. Well, I'm looking, and basically, if I look at my thing here, we have 28 people. We have 22 people that raised their hands. Oh my God. We've got a lot of work to do. This is the first question. All 22 of you got it wrong. The answer is not 30%. I need another brave soul. Eliza, thank you for going. You were being the guinea pig today. Someone else want to unmute themselves and tell me what the real answer is? Oh, come on. This is going to be a long day if this is question number one. Question number one, this is the easy one. This is the easiest one today. No one? All right. Eliza, I am fooling with you a little bit. While it is statistically true, the answer is not 30%. The official answer is less than 30%, because there is a probability, albeit very, very, very small, that the stock market could not change. So do not say it is equal to 30%. The answer is not equal to 30%. The answer is less than 30%. Again, it's very unlikely. The chance will stay the same. It's 0.000000 something, but it is a probability. Phew. Everybody's now like, oh, thank God, man. I thought I was going to go down the dumper in the first question.
Professor?
Student.
Is it less than 0.3 or less than n equal to?
Well, it really should be, again, the question says, what percent of the time does it go down? It should be less than 30%, because you've got to account for there's some probability that it could stay the same. Now, again, on an exam, I am not going to be that exacting. I will post the answers to this answer set, this homework, and the answers say about 30% is what it says. Again, I'm trying to be exacting because I'm trying to teach you the lessons, okay? You know, many of the calculations we do in this class, again, I tell people, do not give me answers with long decimal places. We're not building rockets, right? We don't be that exact. However, we want to be relatively correct because, again, you want to know the formula. You want to know why it is something, right? Later in the semester, I'll talk to you about, there's a coefficient, meaning a number that we use to multiply things, right? And that number we use is 1.96. In 222, which is the next class you'll take after this one, they don't use 1.96. They relax that number to be equal to 2 because it's close to 2, which is fine. But the thing is, you want to know really why it is 2, right? So it's kind of annoying. And again, I teach this class. I teach a version of this class and 222 to the graduates. And I ask, and again, it's a formula that you use all the time in class, and it's got a 2 in it. I ask them on the midterm, what's the 2? And what does it mean? And again, I want to make sure you understand what that means. So I want to have you an idea to understand the mechanics. Again, Uncle Al's behind my shoulder. He's very inquisitive. What's that mean? Right? And again, he wants an answer in a simple form. Can you explain it so Uncle Al gets it? Okay. All right, let me go. You're gonna not see my video, my face for a while. Maybe that's a good thing. And I'm gonna share my document camera, and we're gonna continue with the problems. Okay. So again, I've got a blank screen here, and I'll try to make sure I write big enough. Obviously, if you can't see it or it is blurry or whatever, make sure I just, again, please don't stand on ceremony. Feel free to interrupt me, right? So again, do not send me a chat because I won't necessarily see it. So if I'm talking too fast, or if you don't understand a word I said, or if you want to tell me that there's a big bug crawling on my shoulder or something, feel free to tell me. All right, okay. So the second problem says that an insurance company analyzes that on 50% of the days, they see at least 2 accident claims, right? So let me see how big my camera is here. There we go. So the probability of at least 2. So X greater than 2 is 15%, right? Does this mean that 100% of the days, so 100 minus 15 or 85%, is that the probability that it receives less than 1 accident claim, right? So is that true? So is it 85% that X is less than 1? The number of claims is 0.85. Is that true? True or false? Again, today's class is one of the few classes where there's a lot of chances for people to participate. All right. Now I can see a lot of people are straining to see that. So let me see if I can change my. Is that a little better if I do it in the blue? Thumbs up if it's better. All right, great. I want to do that. All right. So let me change this then with you. All right. Okay. There we go. Is that a true or false statement? Somebody unmute yourself and tell me.
That's false.
Why? Why?
Because there could be the chance that it's one case.
Right. Exactly. What is missing is the probability that X equals 1. Exactly. Right. Again, these two things are not collectively exhaustive. Right. Again, the sum of all the probabilities does not equal 1. Right. And you forgot something. Right. So clearly that is not a good statement. Okay, problem number 3. Which do you think would be a better news to hear? That someone calculated you have a 90% chance of making a profit, or someone calculated you have a 110% chance of making a profit? Which is better news? Don't be bashful. Again, if you have your blue hand up, put it down or put it up again, because I don't know if it's up from the previous problem. Rochelle, you want to answer that problem?
Yeah, I think 90, because you can't have over 100%.
That's exactly right, right? 110%. What does that mean? That's like, hey, the chance of rain is 120%. What does that mean? You're underwater? I mean, it doesn't make any sense, right? Clearly, right? You can't do that. Yes, that's exactly correct. Okay, good job. Okay, next problem is a quality inspector selects 5 random components, remove them one at a time from the 20 working components. All right, so what you do is you have a box, right? And in this box, you've got 5 defective components.
Professor, we can't see your doc.
Oh, thank you. I forgot. Thank you very much. Can I go back and forth? Thank you. You get 5. You got a box. You get 5 defective components, and you get good ones. So your N, your sample size, is 25, right? So it's 25 total. All right. So the problem is, what's the chance of selecting? You're gonna reach in there and choose 5 components, right? So you want to know what's the chance of selecting all defective components. Now, I do not want the answer, right? I don't want the answer of 0.37. I want you to tell me, how would you calculate it? How would you tell Uncle Al how you would calculate that answer? Anyone? How many in the box? Oh, who's going to do it?
It's 5 over 25
5 over
times
25.
times 4 over 24
4 over 24.
times 3 over 23
3 over 23.
times 2 over 22
Yep.
times 1 over 21.
1 over 21. Okay. Is it GS1? Did I say it correctly?
Oh yeah.
GS1. Okay, great. All right. You said multiply. Is it multiply? Do you multiply these together or do you add them?
I multiply it together.
Why do you multiply them?
Because they are not parallel. I do not know how to explain.
Someone want to help her out? Why do you multiply or add? And you're talking to Uncle Al. Do not say the addition rule or the multiplication rule. Uncle Al doesn't know what that means.
Because they are independent.
Independent?
Yeah.
That is true, but again, Uncle Al is confused. Independence to him is 4th of July in this country. He doesn't know what that means.
Like those 5 events have to happen together somehow.
Say it again?
Like those 5 events have to happen together at one time.
Okay, I didn't really understand you. Again, it's a bad connection. Anyone else?
I think he was trying to say that the events have to happen together, not like one at a time. Or
Okay.
like it's not just, you don't want just one defective one out of all 5 draws. You want them all to be defective.
Okay. So again, Uncle Al is confused. Why are we adding? Why are we multiplying, not adding? Again, you are all correct, but again, that's not a way to explain it simply.
Oh, because she is using the rule like PA and B equals PA times PB. So
that's correct.
In
that's
this
correct
case,
too.
like if you want all 5 is defective, you should like times them.
Okay.
Because these 5 defective components are independent.
Okay. All right. Again, what you're saying is all true. Uncle Al is going, I have no idea what they said. Explain it simply. This is the way I explain it. Uncle Al, listen up, buddy. You know basic probability. Tell me which is more likely to happen. Is it likely that I reach in that box and I choose one item and it's defective? Or is it going to be more likely that I reach in there 5 times and pick out all 5 defectives? Oh, clearly, the first one is going to be more probability. It's going to be less likely to choose all 5. Very good, Uncle Al. Okay, very good. So, Uncle Al, clearly, if we know, if we know that's going to happen, if we add these, the probability goes what? It starts increasing. We don't want to increase. It's got to decrease. The only way we can get it to decrease is by multiplying. Oh, now I get it. Right? Again, I don't care whether you know the rules and can quote the rules to me. That is useless. I want to know, can you explain it to somebody that may not have a strong understanding of statistics? Right? So if you can explain it logically, that's going to help you memorize it, right? So now everybody in this class is going to get this right. And you don't even have to memorize any formulas. You just know, hey, the probability is got to be decreasing. And when talking about fractions, the only way to get fractions to be smaller is by multiplying. If you add them, they get bigger. Next question. What's the chance of getting all not defective?
It would be like 20 over 25 times 19 over 24 times 18 over 23 times 17 over 22 times 16 over 21.
That's correct. And again, you're multiplying because the fraction needs to decrease. Correct. All right. Next question says, what's the chance the fourth component selected is defective, given at least three components, the first three have not been tested yet? What's the probability the fourth component is defective, given the first three have not yet been tested?
It's 2/22.
It's what?
2/22.
2/22?
Yeah.
That is incorrect. Right? This is the notion of independence, because the idea is you don't know the first three, so this is the first one you're gonna look at. Okay. So imagine I have this box. What I've done is I've reached into the box, I've taken three of them, and I've jammed them in this corner. Then I take this one here, and I take one out. This is the first one I've seen. So clearly, how many are in the box? 25. The fact that I put three in a corner, who cares? It's still 25. How many of the 25 are defective? 5 of them. So it's 5/25. This is a great notion to understand something has to do with independence. I have here a deck of cards, right? Okay. Now, to make sure we're all on the same page, how many cards are in a deck of cards? How many? Anybody know?
54.
Not 50. 54 with the jokers. How many without the jokers? 50.
52.
52. How many suits are there in a deck of cards?
4.
4. How many cards are in each suit?
13.
13,
13.
right? So 52 cards, 4 suits, 13 per. We're going to be doing a bunch of card, as you did for the homework, probabilities to do with cards. So it's good to know that, right? So 4 suits, 13 cards, 52 cards. Okay. So here's what I have here, all right? So what I've done, all right, you can hear me in the background. I've shuffled these cards, okay? Now, what is the probability that this card right here is the 6 of clubs? What's the probability this is 6 of clubs?
1 out of 52.
1 out of 52. Correct. Okay. Now, what we're going to do, all right, so 1 out of 52. What if I take this card, and I'm going to show you what it is, right? I take this card, and I'm going to put it down in front of me, and let's say I give this to, we're going to call this person Bill. I give it to Bill. So Bill has that card. So now I have only 51 cards left. Now, I have a card. I ask Bill, I say, Bill, what is the chance that this card is the 6 of clubs? What is his answer going to be?
Uh, 1/51.
Correct. Because he already knows this card. And since he knows this card is not the 6 of clubs, he knows there's 51 left. He knows this one. Okay. So Bill has this card. What I'm going to do is I'm going to give 2 cards, this one and this one, to Susie. Again, here's Bill, and here's Susie. Okay, Susie. Now what I'm going to do, I'm going to ask Bill, here's this card. Again, you can see what it is. Bill, what is the chance that this next card I'm going to draw is the 6 of clubs? To Bill. What does Bill say?
1/49.
Why does he say 1/49?
Because he.
Again, what does Bill know? Bill knows only this card.
So it would be 1/51.
Correct. The fact that Susie has these 2 cards, he doesn't know what Susie has. So to him, this probability that's in my hand has going to be 1/51. So I asked Bill, what is the chance that this card is a 6 of clubs? He says 1/51. Everybody understand that? Because the next question is going to be tricky. Now what I do, we just heard Bill's answer. Now here's Susie. Susie knows what her cards are. And I asked Susie, what is the chance that this card I have holding up is the 6 of clubs? What does she answer? Think of your answer carefully.
1/50.
1/50? Who said that? Caitlin? It's not, you're very close. It's not 1/50. Why is it not 1/50? Again, yep, Caitlin, yep.
Okay, because she doesn't know what his card is, so.
But again, he just answered. I said, Bill, what's your, and he said, oh, the chance is 1, because clearly if he had the 6 of clubs, he would say the chance is 0 because I have the 6 of clubs. So he doesn't. So Caitlin, back to you. What is Susie's answer for the probability of this card?
1/49.
That's correct. That is correct, right? This gives you this helps exemplify the notion of independence. Okay? Because again, here's what it is here, right? And here's what he has here, right? We all know that this is not the card, right? But the thing is, with this deck right here, I know the 6 of clubs is right there. Professor Parker is good. Normally I get some applause when I do that. Oh, geez, make me feel loved. Come on. Yes, simple little trick. All right. Now again, if your probability is, cards are a great way to understand probability, right? So certainly there's lots of ways to look at cards and understand how to do different things, right? So I mean, because a lot of different ways you can look at and demonstrate some of the notions that we learned yesterday with using cards. Okay, and again, we're going to do more with cards later on in this class, looking at the homework. Okay, good job. So again, the answer to this problem we just did is 5/25 because it's independent. Because even though you have this box, right, and you got 3 of them over here, you're still taking it's still your first draw. You don't know what you're getting, so it's still going to be independent. So it's still 5/25. Okay. All right, moving on. Next problem says in the lottery you choose 3 different numbers out of a list of 20 possible numbers. The lottery then selects 3 of the random numbers that to be winners. What is the chance all your numbers are selected? Right.
One over 8,000.
Again, don't give me the answer. Tell me how you figure it out.
So you got 3 numbers to choose, and there are like a set of like 20. So
Okay.
you're gonna have
So again, so the first one is 20, right? So what's the chance the first draw is one of your numbers?
1/20.
Not one. It's not in a specific order, right? Because if your numbers are 5, 6, 7, it could be any one of the 3, right? And then how many are left? 19. Out of the 19, how many meet your criteria? Only 2. And then the third one, there's 18. How many meet your criteria is 1. And again, you're multiplying, not adding, because it's got to be smaller. So that's going to be your answer.
Professor.
Yep.
But you would get like a really small number, right?
Yeah. Which is why lotteries, no one wins. Right?
Yeah.
I mean, it's so funny. You look at people, you get these national lotteries where you can win millions of dollars, right? So, you've got to go out there, but the odds of winning are so small, right? So, in this country, in the U.S., right, they have a Mega Millions and a Powerball, all that sort of stuff, and some of the payoffs are millions of dollars. But the problem is the chance of winning is so small because you have to have all these numbers selected, right? The chances of winning are staggeringly low. In an analogy, you have a better chance of being struck by lightning twice than winning the lottery. Right? You have a better chance of being struck by lightning twice than winning the lottery. Now, that being said, I'm not saying don't play the lottery if you don't pay the lottery. Obviously, if you don't play, you can't win. But certainly, there's no strong benefit in going out and buying 20, 50, 100 tickets, right? Yes, you can increase your odds, but you can't increase your odds dramatically to make it worth it, right? So I mean, people always ask me as a statistician, I say, yeah, if it's a big payout and I think about it, yeah, I'll put down $1 or a couple of bucks, but I'm not buying many tickets. I may have one ticket knowing that I'm not going to win for that 1 in a million or 1 in a billion chance that I win. Okay, that's great. So believe me, if I'm not here tomorrow, you know what happened. Okay. All right. So that's the thing. All right. So continuing on, what's the chance that at least one of your numbers is selected?
I use 1 minus neither of them wins, so it's
1 minus
17/20 times 16/19 times 15/18.
My apologies. I'll get a better pen for tomorrow. Why?
Because the probability of neither of them wins is 17/20 times 16.
Yeah, I know, but why? But why? Can you explain to Uncle Al why you did this?
Because well, I think neither of them wins plus either of them wins must to be equal to 1.
Right? It's really 1 minus none. So when you say at least 1 implies 1 minus none. So 1 minus, because 1 is 100%, 1 minus none of them winning, meaning 1 minus not getting anything that is in your selected is in your answer set, by default tells you that you're going to get at least 1 number. Again, if your numbers are 6, 7, and 8, right? It's this probability that you get at least one of the numbers. So that means you may get a 6, you may get just a 7, you may just get an 8, you may get a 6 and a 7, you may get a 6 and an 8, you may get a 7 and an 8, and you may get all 3 of them right? Those are all versions of getting at least 1. So, right? So this is a key thing to know. If I say something 3 times, it's important. If I star it, that also means it's important. So again, you want to know this notion of 1 minus none. It is going to rear its head a few times in this class. Okay? All right, moving on. Good thing I have lots of scrap pieces of paper here. Next question says, health insurance. A health insurer notices that 70% of its customers have no health insurance, health expenses. In a pool of 5 random patients, what's the chance none of them have any health insurance expenses in a year? Raise your blue hand and let me call on you. Ryan, I'm going to put you on hold because you already answered one. See if anybody else does. Again, I'm trying not to call on the same people. Kaylin, go ahead. What's the answer?
I think it's 70% times 70% times 70% and times 70% times like 5 times to the 5th power.
70 to the 5th power.
Yeah.
That is correct. Right? This also demonstrates the notion of independence, right? Because of the fact that if you're looking at 5 people, right? Here's my 5 people. So if this person, the chance that this person doesn't have health insurance is 70%. The chance that this person doesn't have health insurance is also 70%. It has no bearing whether this person has it, right? So therefore, it's going to be 70% for this person, 70% for this person, 70%, 70, and 70, right? So these 5 people, known as the phalange family. All right. So so it's going to be 0.7 to the 5th, right? 0.7 to the 5th. So that is correct. Well, again, it's kind of hard. I'm trying to show the video camera show me too, because it's kind of want to do both things. Okay, that's correct. Number seven, we're going to skip that one. I'll come back to that one tomorrow. That's a little bit of a harder problem to talk about. So let me do that tomorrow if I have a little more experience. Okay. All right. So the next one, right? What I've got is two decks of cards. Right? So 2 decks of cards. So what the question is asking you is, okay, we're going to take two decks of cards and flip over 2 cards. Right? What is the chance? With a chance that we get no diamonds? Right? So based on what I just did, how do you solve that problem?
So the chance of getting no diamonds would be a 39 over 52 times 38 over 51 times another 39 over 52 times another 38 over 51.
So 39 over 52. Say it again.
Times 38 to over 51. That's for the first, and then you time another 39 over 52.
And then
and then times 38 over 51.
38 over 51. Okay, here's my question. What goes right here?
Multiplication.
Is it multiplication or is it an addition?
Multiplication.
Why?
In order to have, because like you have two decks, and then like the first, honestly, if you add them together, it goes over 1.
Correct. Again,
so.
it must be multiplied because it's what I called iterative. So getting this and then getting this, so getting all 4 cards to meet your criteria has got to be less likely. So again, the probability is going to be decreasing. So it must be multiplied. Again, I don't care whether it's the addition rule or the multiplication rule. What the name of the rule is, I don't care. But you understand, it's got to be multiplied. Okay? All right. The next question says, what's the probability of turning over the cards, right? Trying to get my demonstration going here. What are the chances here that you flip over the cards and you get 1 of each suit? Okay. So what is that probability? Someone else.
1 times.
No, someone else. I want you, Mijan, you already participated. I want somebody else hasn't participated yet today. Chance for people to participate. Again, I don't care if you get it right or wrong. I want you to give it your best shot.
26 over 104 times 26 over 103 times 26 over 102 and times 26 over 101.
Oh yeah, but the thing, why are you doing 104? Because I didn't combine the decks. I kept them separately, right? If I put the 2 decks together, it'd be 104, right? So I didn't do that, right? So if I took these decks and mashed them all together, that'd be 104. But they're separated, all right? So Dimitri, so adjust your answer.
So it's 13 over 52 times 13 over 51.
13 over 52. 13
times,
over 51.
Times 13 over 50 and times 13 over 49.
Okay. You made 2 mistakes. Because again, how many cards in this deck? In this deck, there's 52. In this deck, there's also 52. So you can't, so it's 50, 51. This is still going to be 52, and this is still going to be over 51. Right? All right. Now, you made another mistake. Why is it not 13 as the numerator in the first one? Dimitri is still you. Is it Dimitri or Dimitro? How do you pronounce your name?
Oh, Dimitro.
Dimitro?
Yeah.
Okay. Sorry. Again, I will try to pronounce your name correctly, everybody, but you gotta help me. You know, it may sound rather funny when I try to do it, but I'll do my best. Okay. So I'll give you this question, and I'll go to somebody else. Why is it not 13? There are 13 cards in each suit, but Dimitro, do we care what the first card is? Do we care what suit it is?
I guess no.
Right. No. Don't say you guess no. It is no. Right? We don't care. So really, the first one's going to be 52 over 52. That's the hint. again, so once you determine that this card is a diamond, then what you want to know is the next one cannot be a diamond. So it's not 13 over 51. What is it for the next one? Somebody.
39.
Caitlin, correct. 39. And you get the heart. Caitlin, continue. So then it's what over 52?
26.
26, correct. And you get the spade, right? And then what is it for the last one? It's out of 51. How many is it?
13.
Correct. Right? So Dimitro, you are correct if indeed, if it was, hey, how likely is it that you get the spade followed by the heart, followed by the diamond, followed by, right. If you have a specific order, then that's what it's going to be. But the question says you don't care about the order. All you care about is that there can be no repeats, right? Okay. There's a lesson. There's a lesson in everything I do, right? There's a reason why I chose these problems, right? And there's some subtleties, okay? So one of the things I want to talk about is making sure you read the question, right? The question did not say, okay, this suit, that suit, this suit, right? It just said, what's the answer of getting one of each suit? So the order didn't matter. So what I showed you that was circled, that's got to be the answer, right? So you want to make sure that you're very, very exacting in how you read the questions to read specifically what is being asked, right? And not something that's similar around it, right? So again, this right here is the probability that you're going to get at least, one of each suit, and you don't care about the order. If we want to know about the order, that's a different question. Okay. We're also going to skip number 6 for right now. Let's go to number 13. Number 13 says, poker is a popular card game in which each player is dealt 5 cards, right? So again, let me get one of my decks here, 1 second. Right? Where you're dealt 5 cards. Right? If they happen to all be the same suit, right? All the same suit, that's called a flush. And if you ever get that, that's a great thing, because generally that's a very, the chance of getting that is, again, very low. You can figure that out, actually. How can you figure that out? What's the chance of getting a flush?
It would be a 13 over 52.
Yep.
Times 12 over 51 times 11 over 50 times 10 over 49 times 9 over 48.
Close.
Multiply 4 since the suit.
No need to multiply by 4.
So
Again,
like 52 over 52 and then 12 over 51.
there you go.
Yeah.
Exactly right. So again, Bo, I mean, you were right if indeed I said a flush in a specific suit. I didn't say a specific suit. Just getting a flush, you don't care what the first card is. So once the first card was a 10 of diamonds, then what meets your criteria are all diamonds afterwards. So it's 52 over 52, 12 over 50, 12 over 51. I mean, 52 over 52, 12 over 51, 11 over 50, 10 over 49, 8 over 48. Make sense? Okay. So, so that's what we're asking. So the question says, if you're dealt 5 cards, what's the chance that you'll get a flush? So again, we just did that. So that's 52 over 52, right? I'll write it out here. So 52 over 52 times 12 over 51 times 10 over 50, 9 over 49 times 8 over 48. Okay. So here's my question. My question is, okay, what if two people are playing? What is the chance they both get flushes in different suits?
Professor, can I ask you a quick question?
I have a quick answer.
Why did you skip 11?
Oh, I didn't mean to.
Okay.
Can't walk and talk at the same time. Sorry, this pen isn't really working any better. There you go. Thank you. Sorry about that. Keep me on my toes. That's good. Thank you. What's the chance you get both in different suits?
You multiply that again to that.
All right. Wait, oh, Bo, I'm gonna have somebody else go. You've already answered. Somebody else. Dimitro, you've already gone. Somebody else.
Would it not be just the exact same thing? Like multiply that by the exact same equation?
So Max, so I have this equation. What am I going to do to it?
You would like, I mean, you do the exact same thing again, and then multiply the two sums basically. Like it's.
But I can't do the exact same thing, right? Because if I already have 5 cards to you, how many? You know, I'm not starting with 52 cards.
Yeah, fair enough.
So rather than the first one, so go through it. So rather than being 48, the first one, how many out of how many? Again, start with the denominator. There's out of how many? There's only 47 left, right? How many meet your criteria? The 47.
It'll be all of the other suits.
Right.
No?
So again, so if the first person has diamonds, then this person can get hearts.
So yeah, like
spades or clubs, right? Yeah. So clearly, there's 13 per. There's 3 suits, so 13 times 3 is 39. 39. Yeah. 39. Then take it from there.
From there, it would be. Yeah, I mean, yeah, just. Yeah.
1246, 1145, 1043, and 9 over 42.
Yeah.
So this whole thing is the answer, right?
Yeah. Professor?
So the trick is to understand this one here, and then this one here.
What happened to 45?
What happened to what?
45 for the.
Oh, sorry. Jeez. Yep. Sorry.
Oh, okay.
Again, sorry. 45, 43. You can't count.
How did you get 39 again?
Because if they want to be different suits, if the first person has the first card in diamonds, that means all the diamonds can't be, you know, the second person can't get a diamond. So it's going to be any one of the remaining 3 suits. Again, cards are a great example. Tao, are you having a party back there? Because you're definitely laughing at somebody in the background. It can't be me. I'm not that funny. Yes, Dimitrov, question. Or oh no, do you have your blue hand up? Okay, there you go. Okay. Okay. I want to do something for a minute. All right. So the idea is we've talked about probability, and we've talked about, you know, how to look at probabilities and how they would affect your behavior, whether you have health insurance, whether you're going to win at card games, all this sort of stuff. Okay, so now I don't on your screens. Do you just see me, or do you see the thumbnails of all the other people in class? What do you get to see? You get to see everybody?
Yes.
Yeah. So you get to see. So Caitlin, you can see everybody else in class. Okay. All right. So all right. Here's my question. Look to your left. Look to your right. Right. What is the probability? What's the probability that tomorrow is one of those two people next to you birthday? How many days in the year?
366 this year.
365. 365 days a year. How many days can be your birthday? So the probability is what? 1 over 365. All right. We don't need to calculate it. But my question is that a big number or a small number? Small number. All right. Let's play a little game. There are 28 people in this classroom. I'm going to ask you a question. The question has 3 possible answers, multiple choice in this game, multiple choice. Answer A is going to be, that's going to happen. Without fail, I can almost guarantee it. Answer B is, it might happen, but probably unlikely. Answer C is, that'll never happen. Again, A is, that's going to happen. B is going to be, it might happen, not likely, like, maybe 5% maybe or less. C, that'll never happen. Okay. We just determined that the chance of a birthday is 1 out of 365, which is not much. Here's my question. My question is, we're going to go through this Zoom room. There's 28 of us. How likely will we have a match of the birthdays? Again, not year. I'm saying month and day. So is that, that's definitely going to happen. It might happen, not likely. That's never going to happen. That's your answer. Right? So everybody choose your answer. Don't tell me out loud, just choose your answer. And I will choose my answer too. All right. So that's what we're going to do. We're going to go through and ask everybody their birthday. Right? Now, I don't know. So right now on my screen, I am the second picture. What do you guys see? So Ryan Eugen, who are the pictures to your right and left?
To my left is you, and to my right is House Run Song.
Okay. All right. So basically, I'm going to call on people because obviously I can't have you go in order because obviously we all have different pictures. All right. So actually, this is the way I'm going to do this. Use the attendance list. Great. So actually, no, I can't do that because some people aren't in here. All right. Well, no, we'll do this way. Okay. So again, Max Zhao, when's your birthday?
It's 9th March.
9th of March. Now, anybody else have the 9th of March? If you have 9th of March, unmute and says, that's me, go crazy. No one. Okay, Bo, what's your birthday?
December 12th.
Okay. Anybody? Mijan?
Yeah, my birthday is December 12th.
Who is?
Me.
Raphael?
Yeah.
That was only the second person.
Yeah.
Oh my God, that's crazy.
Wait, were you all saying my OB class?
I think so. Yeah.
Yeah.
Why? Did you guys do this in OB already?
Yeah.
No, well, no, but we like know each other from OB.
Okay. Oh,
Yeah.
well, there you go. And you have the same birthday. Well, we
Yeah,
can't
I guess
start.
so.
We can't stop there. Mijan, what do you have? Mijan, what's your birthday?
December 13th.
Maybe have December 13th? Okay. Next, Eliza, what's your birthday?
October 26th.
October 26th. Anybody? How's Sean Song?
October 17th.
October 17th. Close. Mine's near then. Mine's not that day. Tao, what's your birthday?
Oh, mine is October the 28th.
October 28th. Okay. Ryan? Nugent?
Mine is on October 1st.
October 1st. Kaylin?
May the 22nd.
Anyone? Okay. GS1? She?
March 14th.
Okay. Rochelle?
November 5th.
November 5th. Uh-oh. Max? Sweet Bomb.
March 16th.
Oh. Okay. Oscar?
August 24th.
August 24th. Okay. Ashley? Ashley Pung?
October 11th.
Oh, gosh. Another one. Okay. Des Pun?
November 9th.
Okay. Ryan Hong?
September 30th.
September 30th. Okay. Raphael, we know yours. Caitlin?
December 19th.
December 19th. Dimitro?
November 12th.
Okay. Eli?
April 28th.
April 20th. Okay. Jeremiah?
April 10th.
April 10th. Maha? Is it Maha?
Yeah, it's Maha.
Okay. Yeah. What's that?
February 24th.
February 23rd. Okay. Hugo?
April 22nd.
April 22nd. Okay. We just reset everybody. Hold on a second. Lucille?
September 23rd.
Okay. Anchita?
It's December 18th.
December 18th. Bo, we have. Max, we have. Ryan Lynn?
May 16th.
Okay. Jiayu, rather, sorry. No? Not with us. Okay. All right, so we only have one. Well, what did you think? How many had said that's going to happen? Anybody? Oh, a bunch of people. Okay. Maha, why did you say that was going to happen? Or have you seen this before? I can't hear you. You've seen it before? Okay, then you can't do that. You can't answer that question. But do you know why it happens? No?
I forgot.
Okay. Who also said it was going to happen? Ryan, why is it going to happen?
Because most of the classes or groups that I've been in, it's always happened. That's just, it's not a math explanation. It's just.
No, that's incorrect. It is 100% a math.
Oh, oops.
It's a statistical analysis. Okay.
I remember it had something to do with the pigeonhole principle.
Pigeonhole principle?
I think.
Oh, I don't know. I don't know that one. Okay. All right. Essentially, I'm going to explain it to you. It's essentially like this. Okay. Here I am, and here's the person sitting next to me. And then here's everybody else. right? So essentially, we're trying to see whether we, me, and Susie, right? We're trying to see whether Susie and I have the same birthday. So before this person speaks, the chance that I have a match with this person is what? 1 out of 365. But once this person speaks and says their birthday as December 18th, the chance that Susie and I, right? The chance that we have the same birthday is 1 over 365. But once we know that neither of us have 1218, the chance that we have the same birthday has gotten better. It's now 1 out of 364. And then the next person says their birthday, and it's another day, and neither Susie or I say that we have the same birthday. Guess what? The chance we have the same birthday gets better. It's now out of 363. Next person, 362. Next person, 1 out of 361. Next person, 360. It keeps going like that, right? So the chance of having another birthday once people start telling their birthdays gets better. So really the formula, and you can figure it out, it has to do with the 1 minus none, right? So what it is it's 1 minus. So let's say there were 20 people in this class, right? So the numerator would be 365, right? And then it's 365. And then the next person would be 364, 365. The next person sees 363, 365. Next person 362, 365. And you subtract 1 until you do that. 20 people do that 20 times. Right? So really it's 1 minus 365 times 364, 363, dot, down to 340, 346. Right? And the denominator is what? 365 to the 20th. Right? Right? So this is for 20 people. So what happens is, again, remember we did this problem in class. The chance of you not having health insurance, getting 5 people, 5 random people with no health insurance is what? 0.7 to the 5th. So the chance of you having, the chance that it's your birthday is 1 over 365. If there's 20 people, it's 1 over 365 to the 20th. That's why I wrote the 20th here, right? So you can actually do this out. So again, the issue is the number of people in the room becomes this exponent here, and then you take off 1 for every person in the room from 365. So what happens is once you get to be 24 people in a room, the chance of having a match is 60% or greater. So again, it's better than half. And then if you get like 30 people, it's now like 73%. If you get like 40 people, it's almost 80%. So it actually has to do with it has to do with the number of people. So that's why I told everybody there's 28 people in this class. So I knew there's going to be at least 1. I was hoping there was going to be 2, but it can happen. So again, this is a very common party trick, or very common. Again, you're probably going to see this again. They have other seminars where people do this stuff, and they kind of do this for fun to show people. So again, it's very similar. Okay, so I'm going to ask a question another way. Now what I want to do is I'm going to use my deck of cards here. Again, these cards are new. So now what I'm going to do, I'm going to change the game. It's the same game, meaning that's going to happen, that might happen, not very likely, or that'll never happen. But now I want to be more exacting. I'm going to take the top card and I'm going to flip them over. And my question is, how likely will they be a match? Meaning the exact same card. Right? So we'll see if that's going to happen. Oop, 2 3s. My card, get my deck separated here. My hands are getting tired. Uh-oh. I don't know, man. Ah! Oh, so close. Ah, didn't work. But that also normally should work, right? And again, it's probability, so it's not going to work every time. But again, it's the same notion. So basically, what you would do is it's going to be 1 minus, and then 52, 51, 50, 49, dot, 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 all the way down to 1. And it's going to be over 52 to the 52nd. So when we do that probability, it's approximately, I think, 64%. So again, it's not a sure thing, but it should happen 64 out of 100 times. Again, had we done this in class, in person, I would have done it in front of you. And usually it does work. Again, it didn't work today, but again, it's probability, so it doesn't always work. So not as good of a demonstration as I wanted to be, but it's kind of fun to understand how this works. So again, it's basically another example of 1 minus none. Okay. All right. So that we're done with our first portion of class. Let's take a break. Come back, and we'll talk about our discussion for today, which is Bayes' rule. All right. So see you all in a few minutes. I'm going to get myself refresh my coffee.
Hi, Professor.
Yes.
I'm still here. Yeah, I just want to ask a quick question. So we never consider jokers when we're talking about poker, right?
I can't hear you. I'm getting every other word.
So we never consider jokers when we're talking about poker, right? So the maximum is 52.
Yeah. With poker. What about poker?
Yeah.
No. Again, unfortunately, I can't hear you. I mean, it's cutting out like every few words.
It is kind of clear.
Oh, poker?
Yeah.
I mean,
So
are you asking me, can you calculate probabilities when you play poker?
No. I just want to make sure that the maximum of poker is 52, but not 54. So there's no misunderstanding.
I'm sorry, I can't hear you.
Okay, then I'm better to.
Yeah, why don't you send me your question in a chat, or send me your question in an email, and I'll answer it.
Yeah. Okay. I see.
Okay, can everybody see the PowerPoint? Thumbs up. Good. Show me the love. Big wave. Hello. How are everyone? Glad to have you all with us today. Right. This is great. Okay. So I'm going to talk about our lectures today, talking about Bayes' rule. Okay. Let me have a little more sip of my coffee here. All right. 1 second here. Let me check a couple of things. Bryce, put in your last name. I'm not sure I know who you are. I'm trying to take attendance. And the same thing for Lucille. Edit your name and last name. I don't know who you are either. And Jiayu, I don't have your last name either. So if you just edit your name, so until I get to know faces, that will definitely help me with stuff. So kind of put your last name along with your nickname, if you will. That'll help out. Okay. All right. So today's topic is talking about Bayes' rule. Okay. So Bayes' rule is an interesting little adage that deals with probability. So what we have is from yesterday, and let me get my pointer. Right. Yesterday in class, we talked about the fact that basically these are when you have a Venn diagram, the probability of A and B can be seen as A given B times probability of B, or B given A times the probability of A. Because obviously, looking at the intersection of a probability, it doesn't make any difference whether you say, oh, I'm having coffee with cake or having cake with coffee. In either case, you're having both of them. It doesn't matter which order you say them in, right? So that's basically what we're learning here. So the thing is, what you can do is, because whether you say probability of A and B is the same as probability of B and A, you can set these two parameters, if you will, or these two equations equal to each other. So what you can do is set them equal to each other, which is what I have right here. I'm underlining with the laser pointer. You can underline them. Then what you can do is, through algebra, and you do substitution, is you basically, what you can do is you can get rid of the probability of B and divide both sides by that and get the resulting formula. The resulting formula that is in the rectangle that I'm highlighting with the laser pointer. That is Bayes' rule. Bayes' rule is the probability that A happens given B happens, is the probability that B happens given A happens, times the likelihood that even A even happens, divided the probability of B. Now again, it sounds hard to understand when you're looking at just in the scientific format, so we're going to use a couple of examples to show us what it means, right? But what you want to know really is, with Bayes' rule, I mean, it's this simple. It's basically the derivation is just from this statement that came from the PowerPoints yesterday, right? We're setting these two to be equal to each other, and then through substitution, right? And we can basically alter the equation to be what is down here in the rectangle. So therefore, what you really have is you have this form here. This is the exact same one that's on the previous slide. Or you can expand the denominator. You can expand the denominator to be this down here. That's the probability of B happening when A happens, times the probability that A even happens, plus the probability that B happens when A does not happen, times the probability that A will not happen. So clearly you can see that the P of A and P of not A have got to be complements. Again, P of A and P of not A have got to be complements, right? Based on what we talked about yesterday. So what we have this thing up here, which is called Form 1 of Bayes' rule. And this one down here is very simply called Form 2, right? So this slide right here is an important slide. In your notes, it looks like it's page 32. You definitely 100% want to know and have this formula at your fingertips. So again, I said yesterday that one of the key things you can do to prepare for this class and get ready for exams is not rely on things being in the book, but taking them out of the book and putting them onto a sheet of paper to be, quote unquote, a cheat sheet. This is one of them that should be on that sheet. Okay. All right. So basically what we're going to do is we're going to put this formula to use in an example. Okay. So again, what you may want to do is on a piece of paper here, if you haven't done already, you may want to kind of write down these formulas a little bit just so you know what they are, because I'm going to use them in my discussion. Okay. So in our example, what we have is we have a prototype example. So we are saying assume that 1% of the people in a region have a disease. A new diagnostic test is discovered which gives a positive indication 97% of the time the person has the disease. It gives a negative indication 95% of the time an individual does not have the disease. If a individual chosen at random gets a positive, what is the probability that he or she actually has the disease? Okay. Okay. Because again, the test is not 100% accurate. It always says you get a 97% chance of having the disease, given you have a positive. So there's a chance, there's a 3% chance that if you get a positive, you actually don't have the disease, right? And if you have a negative, it's only 95% effective that actually is a negative. It could actually be a positive, be a false negative. So then what we do is we write down what we know. So here we are. So again, we've identified our variables. D is going to be have the disease. Not D is not have the disease. Positive is a positive indication. Negative is a negative indication. So based on what we have on the previous slide, again, based on this information right here, we can figure out this bottom part. So the probability you have the disease is 0.01. Therefore, the complement, the probability that you don't have the disease, again, D bar, is 99%. The probability that you get a positive given you have the disease, again, given you have the disease, the chance of getting a positive indication is 97%. Therefore, the complement is the probability of getting a negative given you have the disease is 0.03. So let me leave where the pointer is right now. That's critical. Many people make the mistake, and what they do is they say, oh, positive given not get the disease, and then they say positive given not have the disease. Those are not complements. The complements are the second thing. The given stays the same. So again, positive given you have the disease, the complement is a negative given you have the disease, right? Many people make this mistake, okay? Therefore, the second thing is the probability of getting a negative given you don't have the disease. Again, the state of nature that must be true is you don't have the disease. The chances are that you get a negative given you do not have the disease is 95%. Therefore, the chance to actually get a positive given you don't have the disease is 0.05, right? This one right here, this is known as a false negative, a false negative. There's a 3% chance when you have the disease that you get a negative, which really is a wrong indication because you really do have the disease. Down here, this is a false positive. There's a 5% chance that given you don't have the disease, the test will say, oh, you do have the disease. Oh my gosh, I'm worried. And you really don't have it, right? Now, to put this in context of what we're going through now in this pandemic, yes. In all of the research they're doing now for trying to find a vaccine or something, they are dealing with false positives and false negatives. I mean, it's just a matter of nature. I mean, it always exists. Now, ideally, you try to get down the false negatives and false positives. You want them to be very, very small percentages, right? There are people that will go in for cancer screenings, and the cancer screening will come back and say, oh, you don't have the disease, when really the people do. It does happen, right? Again, the probability is a probability. I mean, it's a likelihood it'll happen. Okay, so our question we want to answer is, how likely, if you actually get a positive, how likely do you actually have the disease? Okay, you will see a question like this on the exam that we're having a week from Thursday. There may be a couple of questions. One of the issues in this course is some students will take the exam and not do as well as they wanted. And they will talk to me and they'll go, Professor Parker, oh my gosh, I got to problem number 4. I just didn't know where to start. Well, that's one of the issues. That comes back to my comment, do you understand what it means? One of the things that you need to be able to do is you need to be able to look at a question, never mind trying to solve it. The first thing you've got to do is be able to understand what type of question it is. Okay? All right? So tonight, you're going to do a bunch of homework problems doing with Bayes' rule. The first one is probably going to take you a little bit of time because it's the first one you've ever done. And you're going to, you're going to fumble around with it, and you're kind of, take it 10 minutes, whatever, and you're going to get it. The next question is going to be easier because you know that all the problems for tonight deal with this one topic. So essentially, once you get the first problem, then essentially you do what I call plug and play. You take the formula from the first problem, transpose it to the second problem, change some of the numbers around, and then you'll get it. And then the third problem, you do it again. Okay. When doing that for homework, that's easy because you know tonight's homework is all the same topic. On the exam, it's not going to say, this is a Bayes' rule problem. This is just going to be a random problem. For some of you, this may be problem number 1. For some of you, this may be problem 18 on the exam, right? So it's going to be all mixed up. So the exam's not going to go in order. So the challenge is to look at a problem and go, okay, that's a probability problem. Oh, that's a Bayes' rule problem. Oh, that's a counting technique problem, right? So that's part of what you got to do. So that's why one of the things in doing the homework is about looking at the homework and being able to discern what kind of problem it is. Students often ask me, oh, Professor Parker, are there more practice problems? And my answer is no, there aren't more practice problems. Really what you can do is you can take the existing problems that you have already and you can change them to make them more practice problems. But part of your studying is to learn and trying to make sure you can discern what type of problem it even is. That's half the battle, right? Okay, so you want to make sure you can do that. All right, so let me go back to screen sharing. Okay, so here, one of the hints that you have is to understand the question asks you the probability of having the disease given you get a positive. So if you look in what you're given, and what you're given is this area up here I'm circling with my laser pointer. If essentially what you're asking is essentially an inverse. Now I mean inverse, I mean you're switching the places of one of the conditional probabilities you're given. Very often that's Bayes' rule. meaning probability of A given B, if you're looking for probability of B given A, you've inversed the A and B, that's Bayes' rule. In this case, we've inverted the disease and the positive. Okay, very good. So this is a dead giveaway. If you see this, oh, this is Bayes' rule. So based on this, what I've done is we've taken the formula from a couple pages ago. We took this formula here, and rather than having it being A's and B's, we changed it to put it in context of the problem. And I always suggest doing that, right? Because if you use A and B, then you have to have a key to know, well, what's A? Oh, A is disease and B is, you don't know. Again, use it. So obviously D very clearly is having the disease, not D is not having the disease. A plus sign is a positive test. A negative is a negative test. Now, to note, you could have a negative is also a not positive, meaning a positive sign with a line over top of it. So you could do it that way too to be consistent. Right? Again, the negative sign could also be the positive with a line over it. Okay. So probability of having the disease, given that you know you got a positive reading, is, again, you kind of invert it, if you will. So it's a positive, given you have the disease, times the likelihood, the propensity that you even have the disease. Again, it's only 1%, so it's very low. All over the probability that you got a positive when you have a disease, plus times the probability of a disease, times the probability that you get a positive when you don't have the disease. Okay? So essentially the denominator is what? It's all the different ways you could get a positive. I'll say that again. The denominator, what I'm circling with the laser pointer, is all the different ways you can get a positive. You can get a positive when you have a disease. You can get a positive when you don't have the disease. Those are all the different ways you get it. So again, they got to be complements. Okay? So once you have this, what you can do is going back to this information here is what I call plug and play. You're taking the numbers that you've already come up with and putting them into the formula. Okay? So 0.97, that's the probability of a positive given you have the disease, times 0.01, which is the probability that you even have the disease outright, only 1%. That is repeated, again, right here, it's up here in the numerator. That portion is repeated in the denominator. So it's 0.97 times 0.01, again. And then the probability of getting a positive when you don't have the disease, again, going back here, that's this one over here. Right? So the first one was this one that I'm circling with the laser pointer. The second one is this one. Again, positive not have a disease, positive with a disease. These are not complements. These are not complements. The complement meaning the state of nature, meaning the D and the D have to be consistent to be complements. So 0.97 and 0.05 do not equal 1. They should not equal 1. They can. I mean, it's certainly possible for it to equal 1, but usually they do not equal 1. Okay? So then you calculate this out, and your answer is 16%. So what that means is if I take this test and I get a positive, oh my gosh, I have this disease, I've got cancer, I've got COVID, I've got something, I'm worried. Well, based on these numbers, the chance of me actually having the disease, even though I got a positive reading, is still, it's only 16%, which is what? 1 out of 6. So virtually every 6 people that have a positive reading, only one of them actually has the disease. Think about that. Every 6 people that get a positive reading, actually one of them has the disease. So if you're thinking logically, you're going, boy, that doesn't seem very good, because what if this is a serious disease or where somebody is, really sick? So you get 6 people think, oh, they have the disease, but in fact, only one of them does. So 5 people really got false information. Yes, Ashley, question.
So
what's the point of the question saying that if you have a positive reading, 97% of the time that's accurate, if that's not the case?
But it's only accurate. It's accurate given you have the disease. So again, that's the next question we're gonna answer, right? So we want to know how based on these numbers, and these numbers are real numbers, the chance we actually have the disease giving a positive is low. Okay, now let's think about that for a second. Why does that make sense? Well, it makes sense because, again, if you have 100 people, the propensity or the probability to have the disease is only 1%. So out of 100 people, you should only have one person. So if indeed I get 5 people that get a positive reading, correctly, only one of them should have the disease because there should only be one person out of the 100. Oh, okay. But clearly it brings up the next question. The next question says, okay, based on this data, does it mean the test is any good? I mean, certainly you want to know, boy, I don't like the fact that there's 5 people that get positives, only one has the disease. So again, you've got, excuse me, 6 people have the positive, only one has it. You got 5 people that are worried needlessly. Okay, so we want to know, how good is the test? What's the correct diagnosis? And that's what CD stands for. CD stands for correct diagnosis. All right. Well, the correct diagnosis is getting a positive when you have the disease and getting a negative when you don't have the disease, right? So going back here a couple slides, right? This is a correct diagnosis. This is a correct diagnosis. Again, these two things here that I'm circling with the pointer, those are correct. This one here is a false negative, meaning it's not accurate. This one here is a false positive. That's not accurate. So it's these two that we want to know about. Okay? So therefore, a correct diagnosis is getting a positive, given you have the disease, times the likelihood that you even have the disease. Again, so that's 97 times 0.01. Plus a correct diagnosis over here is getting a negative when you don't have the disease. That's 0.95 times the chance that you don't have the disease is 0.99. So when you do this, that means 95. What? Yeah. So it's 95% effective. Now, if you think about it, that makes sense. Why? Because this number here, 95%, is weighted so heavily by this portion of the formula. So many people, again, the chance of having the disease is only 1%. It's 1 person out of 100, right? So what happens is the test is very good at predicting negatives. Okay, so what have we learned? We've learned based on Bayes' rule, based on these parameters, and again, the parameters are for this based on these numbers. So based on these numbers, we know that if you have a positive reading, and oh my gosh, you're worried, there's only a 16% chance they actually do have the disease. Okay, that's good. So basically a 1 in 6 chance that I'm actually infected. How good is the test? Well, the test is basically 95% accurate. Again, that's okay. In the real medical community, clearly they don't want 95%. In the medical community, they want 99.99% or 99 point something, right? I mean, with the research they're doing on COVID right now, they want a 99% efficiency rating, right? Or efficacy rating, whatever it's called, right? So, all right. So therefore, knowing this then, knowing that it's 95% accurate, then really, if we're trying to administer this test to people and we want to say, okay, what do we really want to look out for? Really what we want to look out for is the positives. Because the people that get negatives, they're not gonna be concerned. Oh, I have a negative. Okay, well, no big deal. The people that get a positive, they're the ones like, oh my gosh, I've got this disease. I'm so worried. So it's those people you want to know how many people are going to call you. Okay. So we want to go, we suppose those that get a positive will go back for further testing. What portion of those people actually get a positive? So again, so getting a positive is, again, how many different ways can you get a positive? You get a positive when you have the disease, and you get a positive when you don't have the disease. So again, so that is the probability of getting a positive given you have the disease times the probability of having the disease, plus giving a positive when you don't have the disease times the likelihood that you don't have the disease. Okay, so 0.97, again, that's from the plug and play back there, plug and play. So it's 97 times 0.01 and 0.05 times 0.99, which actually comes out to be 0.056 or 6%. Okay. All right. Take a look at what I'm underlining. I'm underlining with the laser pointer. That formula you've already seen before, and it's right here. It's the denominator right here. This officially, this formula here is essentially form 2, right? The probability of getting a positive when you have the disease times the probability of having the disease, positive when you have the disease, positive when you don't have the disease. Now again, we can simplify the denominator in this case to be, that's the probability of getting a positive. Remember, you get a positive when you have the disease, you can get a positive when you don't have the disease. Okay? So, tonight or after class, as you're studying this topic, it's important for you to kind of look at this PowerPoint, go back, see how it relates to this PowerPoint, and understand that really what you could do over here, this one here, this one here, you could have substituted the denominator is the probability of having a positive. Because again, all the different ways you get a positive when you have a disease, you get a positive when you don't have the disease. Okay? So it's a matter of you going back and forth. Again, I'm on the last slide, so it's only like 11 slides. So you could go back and forth and understand how the slides all kind of relate to each other. Okay. So our numbers are the following. 16% of the people that get a positive actually have the disease. The test is 95% accurate. Okay, because clearly the 16% would cause you to have another logical question. Gee, I'm not sure how good the test is, but the test is pretty good. So therefore, we really want to know, all right, how many people are going to go back for this testing? How many people are going to get positives? It's 6%. Okay, let's see if the math works. We've got 100 people. 100 people in a room. How many people have the disease? One person. This is person X. How many people in the room are going to get a positive reading? 6%. 6% of the 100 is going to be 6 people. Of the 6 people, 6 people get positives, how many of them actually have a disease? 1 out of 6, only one person. Person X. Oh, it works. Okay. For homework for tomorrow. There are 5 problems in the online textbook. The first one is problem, I think, 7 or 8. You do 8 through 13 or 7 through 12. I can't remember the number. But you're going to do those 5 problems. In addition, there is a case. The case is called Why Choose Me. If you look on the online resources, there is a section that says cases, and you can look at one. There's one called Why Choose Me. To reiterate, a case problem is essentially a big word problem. The case itself is probably 3 or 4 pages. Do not worry about trying to remember all the names. We're not going to talk about that. When we do the case tomorrow, I'm going to use just numbers. And as a matter of fact, the numbers I just used, that I just showed you for the prototype example, looking at the PowerPoint, this is the case. You will go through this and you'll redo it, and you'll see these are the exact numbers from the case. You'll calculate this, and you'll calculate this, and you'll calculate this. Okay? So that's the first part of the case. And again, it's going to be those exact same numbers. The question is, how does this then translate to the student body? The case deals with an outbreak of the AIDS virus on a campus. There are 10,000 undergraduates, 3,500 graduate students, 150 staff members, so many professors, blah, blah, blah. I'm telling you now, please listen to me. I don't care about the school numbers. We're going to do our calculations tomorrow based on the 10,000 undergraduates complete. Okay? So if we talk about it with the 10,000 undergrads, if you then wanted to do it for everybody in the school, that's okay. Rather than doing 10,000, you do a calculation based on 16,500, whatever the number is. Okay? So in terms of you trying to decide what to do for the homework for this, right? So again, you're going to redo this, and you're going to think about, okay, how would I do this based on the 10,000 students? Okay? Now again, I am going to do this in class. I'm not going to look for any class participation. I'm going to just do it. The case is meant to be a thinker. It's something that you think about and ponder and just kind of, what do you do? Do not spend a long time on the case. Again, 20 minutes, a half hour, 45 minutes tops, great. Do not spend 3 hours on the case. It's not, it doesn't command that kind of time, right? I'm going to show you how to do it. But ideally, by you looking at it and thinking about it and trying to figure it out, most of you probably won't get it. But that doesn't mean you should still think about it. By trying to think about it and getting using your brain, trying to noodle it out, if you will help prepare you for when I do it. Because when I do it, you're going to go, oh, that's so easy. Okay? So it's a way of looking at these problems. So again, so tomorrow's a good indication of a case problem. Why Choose Me will be on the exam. And I'll explain that tomorrow after I go over. So tomorrow, we will begin class by going over the 5 Bayes rule problems that are assigned. We will then jump to do this case. If we have time, again, we didn't cover all the homework problems from today. That's okay. There's many times we will not cover every single homework problem in class. I will post the answers to them. Now, again, I've got to make sure I'm pretty sure I have the answers to the ones that I did today. I'll post the answers. And again, if we don't ever have time to do them in class, sometimes I will, and sometimes I won't. If I don't, you can always come to office hours. If you don't understand, I'll do a problem. But again, that's one of the advantages and one of the things I want you to do by having a study buddy. Again, Raphael, you and Bo obviously were in a class together in the past. Maybe you guys be a study group together, right? So again, I want to encourage you to reach out to other people and set up study groups. If you want me to set up study groups, I can, right? What I can do is I can set up breakout rooms and basically assign you to a study group, and that can be your study group. If you want me to do that, you got to let me know. So someone send me an email and say, oh, that's a great idea. I want to do that. But if I don't hear from anybody, then that means that you don't care. Again, I don't need to spend extra time on things that people don't find valuable. Okay. If you find it's valuable, then I'll do it. Okay. All right. So everybody kind of clear of what the homework is for tomorrow. Okay. Now what I want to do now is I want you to do this problem. It's based on this topic. Okay. Now again, at the end of class today, we could also have a quiz. We don't, but we could. If there was going to be a quiz today, again, it would never be on Bayes' rule. We just learned Bayes' rule in the past 40 minutes. It would be something on probability. Now, tomorrow, at the end of class, if I wanted to have a quiz, it could be on probability and Bayes' rule. So it's always the day, whatever we've covered the day before and prior is always fair game, right? So that is possible. I'm not saying I will, but I'm just letting you know what it is. Okay. So here we got a problem. So take a few minutes. So historically, 90% of all students pass SM 221 or QM 221. Often a student's attendance of discussion section is a good indicator of his or her course performance. From past records, given the student passed the course, 95% frequently attended discussions. Among those that failed, only 10% frequently attended discussions. What's the probability of passing the course given that you frequently attended discussion? Okay, so what I will do now is I will put up the formula for Bayes' rule on my document camera so you don't have to worry about trying to go back and forth. So take a few minutes and see if you can do this problem. Again, my document camera is going to be small, but hopefully I'll already big enough so you can see it. All right, so hopefully you can see my thumbnail. I basically put the formula up there for you as well. Once you're done, put up your blue hand, please. Okay. See if you got this. Right? The first thing I did, which is how I will do every problem in this class, I always write down what I know. The probability of passing the class is 90%. Therefore, the probability of not passing class is 10%. I always have my complements go in the rows. The probability that you want your discussion given you pass is 95%. So therefore, the complement is the probability that you did not go to discussion given you passed the class is 0.05. So the 0.05, 0.95, there's your complement. The probability that you went to discussion given you did not pass the class, or given that you failed, is 10%. Therefore, the probability that you didn't go to discussion given that you failed is 90%. So the question is, given that you went to discussion, how likely did you pass? So again, the state of nature that occurred was that you went to discussion. Now I look up and I see, oh, here is one of my givens. This tells me that it's Bayes' rule. That's one of the hints. So again, the formula is probability, passing given given discussion, discussion, you invert them. So probability of a discussion giving pass times the likelihood even but to pass. This is repeated, discussion given pass times the probability of pass, plus probability of went to discussion given you did not pass times the probability did not pass. These two things here have got to be complements, right? Pass and not pass got to be complements. So if this is 80%, this is 20%. 70%, 30%. 50%, 50%. They must be. Okay, so now I do what's called plug and play. So probability of when discussion if you pass, that's 95%. Probability that you passed is 90%. Repeated, then the probability that you went to discussion if you did not pass, discussion not passed is 10%. And again, I already told you these are going to be complements already, but the fact that you did not pass is 10%. So multiplying it out, 0.855 all over 0.855 plus 0.01. Yeah, 0.01. So 0.855 divided over 0.865 is 0.988, right? So do I have the right answer? I do. Thumbs up if I have the right answer. I do. Thank you. All right, right? So you see how I did it. So I wrote 0.988. So again, on an exam, that's how we want the answer, 0.98 or 0.988. Again, never more than 4 decimal places. Never more than 4 decimal places. Third time, never more than 4 decimal places. And I'll explain why in the course, why we use 4 decimal places. I'll talk about that when I do it later. Okay? Any questions on this problem? You can put your hands down now. All right. Here's my follow-up question. And yes, this is an excellent exam question. Hint, 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 hint. My follow-up question is the following. What is the probability? What is the probability that somebody went to discussion? You're all doing math, and you don't have to do the math. It's right here. The answer is the denominator. Because the denominator here, remember, going to discussion, you go to discussion when you pass the class, and some people go to discussion when they don't pass the class. So this whole thing here that I have in my brackets can be simplified as probably of going to discussion, which is the denominator down here. So it's 0.865 is the answer. That is a great exam question. And again, it shows that you understand what it means. Problems in this class are not necessarily going to be straightforward. Is it 2 + 2 = 4? It's going to be 2 + 2 = 4 divided by 3 to the 4th power. Oh. Okay. We're now done. Again, another class that went almost the full time. That's probably going to be the way it's pretty much going to be. Like I said, I kind of shoot for kind of 2 hours, but again, depending how I feel the learning goes and what I want to talk about, it may go longer. Okay, so we definitely have plenty of things to be done. And tomorrow is going to be a jam-packed day as well. Tomorrow we do some other really kind of cool stuff to talk about stuff with counting techniques. So it'll be an interesting one. Okay, all right. So without further ado, so long everybody. Again, if you want to stay and ask questions, stay on, and I'll answer questions. Other than that, we'll see everybody tomorrow. Have a good day. Enjoy yourself. Stay safe. Thank you.